All right, ladies and gentlemen, this is Graphing of Motion Part 1 for AP Physics 1. All right. Two things that we can get from a graph in physics. The main things we will always be looking at are going to be our slope and our area under the line. So for most basic models in physics, we will use slope. Slope, remember, is rise or over run. Or I like better the change in y over the change in x. So if we use that line formula, y equals mx plus b, m is our slope, b is our y-intercept, and then y is our y variable, and x is our x variable. So using that model and looking at the formula for velocity, velocity is, which is not on your formula chart, by the way, the basic formula for velocity, which is displacement divided by time, or change in x over change in t. That is the formula for velocity. So who gets to play the role of slope if I'm using that formula? Velocity does. Who gets to play the role of the y-axis or the rise? The displacement does. And then who gets to play the role of the x-axis or the run? The time does. So what does that really mean? It means that if you're given a displacement versus time graph, to find the velocity of the object during a specific time interval, all you have to do is find the slope. So the slope of a position versus time graph gives you the velocity. That's a key point to make sure you write down. All right, so here we have some displacement versus time graphs. And sometimes displacement will also be written as position. Sometimes it will be written as displacement. Sometimes they'll even use the word distance. But I don't really like that word, and we'll talk about why later. So what is the velocity of the object from 0 to 3 seconds? So from 0, which is right here, to 3, which is right here, we would need to find the slope of that line. The slope of that line would be the change in y over the change in x. So the change in y is from 30 to 0. The change in x is from 3 to 0. So that is 10 meters per second. So velocity is the slope. Okay? Then, if I wanted to find the velocity from 7 to 8 seconds, which is from right here, the 7 is right here, to right here, notice that's a horizontally flat line. Horizontally flat line slopes are 0. So what does the velocity of 0 mean? Well, it means that it was stopped, or that it's sitting still. And so how long was it sitting still? For 1 second. So now, what's the velocity from 8 to 10 seconds? Well, you have to remember, we have to find the change from the final to the initial, minus the initial. So final, we are 0 minus 90 for our rise, and then we're 10 minus 8 for our run. So they're changing y over a change in x. So we actually have a negative 45 meters per second. So the answer is negative. Well, that's not any surprise since this slope is negative. But what does this value mean? Well, it could mean a couple of things. But it's that the object could be traveling south, or it could be traveling west. Roughly, that would mean that if we were over here from 1 to 3 seconds and we said it was traveling east, then over here from 8 to 10 seconds, it's now traveling west. So roughly the way to think about it is the object is going backwards. This makes some more sense, okay? You should also understand that the slope does not change from 0 to 3 seconds, or from 5 to 7 seconds, or from 8 to 10 seconds. So what that means is it's a constant velocity. It's not accelerating. So that means roughly that your car is on cruise control. Okay, so we had our cruise control set for 3 meters per second, or sorry, 10 meters per second here. And we had our cruise control set for, I don't know, we went from 30 to 90, so it's probably in 2 seconds. So 30 to 90 is 60 divided by, so that's 30 meters per second. And then we went a negative 45 meters per second. So we are stopped, and then we're changing to a constant speed. And then we're stopped, and then we change directions, but we went a constant speed in the opposite direction. Okay? So it's very important that you're able to look at a graph and explain what its motion is in great detail. These graphs can be very conceptual. So if we look from 0 to 9 seconds, now we have a curve. So this actually, so what does the slope do? It's changing. So that means our speed is changing. So it increases and the velocity is increasing, but it's also not constant. If we look at from 9 to 11, then it's horizontally flat. So that means it's stopped. The velocity is 0. And then if we look from 11 to 15, it's a constant slope. So since it's a constant slope, it's positive, so it's going forward, but it's going at a set rate, okay? And so it's on cruise control, but it's still going forward. Then if we go from 15 to 17, now the slope is negative, but it's also constant. So what that means is it is now going at constant speed. I've got it set on cruise control, but I'm going the opposite direction. So I've changed directions. This directional information is going to be huge for us, all right? So let's look at another model. If I use the acceleration formula instead, which is the change in velocity over the change in time, who gets to play the role of slope? The velocity does. Oh, sorry, the acceleration does. I said that wrong. So it's acceleration because it matches in the slope formula. Who gets to play the y-axis or the rise? Velocity does. And who gets to play the time? Or excuse me, I answered my own question. Who gets to play the x-axis or the run? The time does. What does that mean? If you're given a velocity versus time graph, then to find the acceleration, you would use the slope. So the slope of a velocity versus time graph will give you acceleration. Okay? So here we have a velocity versus time graph. These are excellent graphs, by the way. They have the labels, the units, the titles, excellent graphs. So we have our change in y over our change in x, which would be 60 divided by 6 for 0 to 6 seconds, all right? And then from 0 to 60, so that would be 10 meters per second per second. Another way to write that would be 10 meters per second squared, okay? So what is the acceleration from 6 to 9? Well, from 6 to 9, it's a horizontally flat line. So that tells us that the acceleration is 0. And if the acceleration is 0, that means that there's a constant velocity. We're just going 60 meters per second this whole time. So really that's setting our car on cruise control, and that's what it looks like on this graph. So remember on the other graph, a horizontally flat line for displacement versus time meant we were sitting still, but a horizontally flat line here means that we're actually going on cruise control. So we're going to have to start thinking about making sure we pay attention to which graph we're talking about and which axis. Now from 14 to 15 seconds, which is right over here on the graph, okay, we could find the slope, and that would be 0 minus 10 over 15 minus 14, which would give us a negative value. So we'd end up with 10 meters per negative 10 meters per second squared. So this slope right here at the beginning from 0 to 6 is the same slope as from 14 to 15 value-wise, but one's positive and one's negative. What's that actually mean to us? Well, negative acceleration is sometimes called deceleration. In other words, the object is slowing down. Well, we are talking about quadrant 1 here, and I'll go into quadrants at a different time with you. But the object can also have a negative acceleration, and it could be falling, Okay, so in this case, the object is actually speeding up if it's falling, so it can be confusing. So we have to be careful and make sure we understand why the negative sign is there. And right now, it is actually, it's going to help us with directional information. So it could be that it's falling, or it could be that it's speeding up or slowing down, but it does have to talk about the slope. So the slope's positive if it's increasing, if it's going up, and it's negative if it's going down. So we kind of just have to keep that in mind, okay? Now, conceptually speaking, what is the object doing from 9 to 13 seconds? Well, from 9 to 13 seconds is here, and the steepness or the slope, is it increasing or decreasing? Well, according to the graph, actually, it is steeper, but it's in the negative direction. So what this means is that the velocity slows down with a greater change each second. The deceleration in this case gets larger even though the velocity decreases. So it might take a little bit of us discussing this for you guys to understand it. But the velocity goes from 60 to 55, which is a change of 5, and then it goes from 5 to 40, or 55 to 45, which is a change in 10. So it's actually decreasing in speed, but its change in decrease is larger. So that's where the steepness is increasing, but it's a negative direction. So it is slowing down. So it's kind of a different way of thinking about it. So the slope increases, all right? Now, the other thing that we are going to talk about with this particular PowerPoint is the area. So this is the other basic graph model of information that we'll use. So area is base times height for most of the graphs that we're dealing with because they're linear in some way. So when we talk about it algebraically, we'll start with our formula for velocity again. Velocity is displacement over time. Well, I can rearrange that so that it is displacement equals velocity times time. This was actually on your test, okay? So we'd have x equals v times t. So here, who gets to play the role of base? The time does. Who gets to play the role of height? The velocity does. And what kind of graph is this? This is actually a velocity versus time graph, because that's who's playing our x and y axis. So this is the slope of this graph would tell me acceleration, but the area under the line of this graph actually tells me displacement, or how far someone has gone. So what's the displacement during the time interval of 0 to 5? So this is the same graph we looked at earlier for velocity versus time. From 0 to 5, that happens to be area. So what happens to be the area here? So I want to look right here. That actually is a triangle. So we're going to look at it like that. So what's the area of a triangle? 1/2 base times height. So 1/2 base times height would tell me 1/2, 5 times 35, would tell me that I've got a displacement of 87.5 meters. So if I wanted to ask how far I went in the first 5 seconds, I can tell that from this graph too. I could also say how fast I was accelerating at this time too. Now, what is the displacement during 8 to 12 seconds? Well, from 8 to 12 seconds, we have both a triangle and a rectangle. So we'd have to find this rectangle first, which would be 4 times 35. And then we'd have to find the triangle, which would be our 1/2 base times height. Then we could add it all together and find out that our displacement during that time was actually 260 meters. Now, believe it or not, this actually will have a lot to do with a formula we have later on. So I'll be really excited to show you that and how it plays into one of the formulas on the formula chart. Okay. So we could also do it for an acceleration graph, which is a little bit different. But acceleration is velocity divided by time. And I could rearrange that to be velocity equals times, which equals time times acceleration. So what does that mean? Who gets to play the role of the base? time. Who gets to play the role of height? Acceleration. What kind of graph is this? This is an acceleration versus time graph. I haven't actually shown you one of these yet, but we could put acceleration on the y-axis and time on the x-axis, and that would be this type of graph. We will work with these graphs in this unit as well. Who gets to play the role of the area? Velocity does. Okay? So, when we look at these types of graphs, here, if I wanted to say what's the velocity during the time of 3 to 6, find the area. It's a big old rectangle, so base times height, and the velocity would be 18 meters per second. Notice this was constant, so that was easy to figure out. All right, so in summary, there's 3 types of graphs that we're going to deal with. We're going to deal with displacement versus time graphs, or position versus time graphs. We'll deal with velocity versus time graphs, and we'll deal with acceleration versus time graphs. Remember, what's on the y is always listed first, what's on the x is always listed second. Time is always on the x. Okay, and there are 2 basic models that we'll look at when we're dealing with these 3 graphs, and we'll always look at what we can tell from the slope and what we can tell from the area of these graphs. Okay, so the area is under the line and the slope is of the line. Okay, hope you have a great evening. This is a summary, and I probably will talk about this a little more in class, but if you, and we'll talk a little bit about quadrants more in class, so remind me to do this in class. All right, you guys have a good one. Have a great day.